Hello and welcome to this video. I want to show you how to set up and to run the agent-based Microcystis model. The model was published by Freddy Helwiger et al. In 2022, and you can access the model at the GitHub page from Freddy Helwiger or direct download it from the science website where it was published for the first time, which I want to do now. Therefore, we need to go to the acknowledgement sections where we have the paragraph with the data availability and the link to the Zenodo website. When we go to the website, we see that we have a zip folder which we can download down here. Once it is downloaded, we can access all the files which are within the within the folder, which I just copy paste to the folder of my choice, in this case an example folder. Within this folder we now have all the information we need, including the code and also the Excel files. So the code is written in Fortran and executable in Excel. Therefore, we have different Excel files which we need later. The model file where the code can be executed using the Visual Basic. The 1F2, which is includes all the input and output for the model, and the figures where the output can be depicted in the end. We also have a README file with all the instructions that we need to set up and run the model. So before we can start, we must make sure here's first of all like a table with all the files included and the description of it, so you can double check. But what I wanted to say that we must make sure that the settings on your computer are right. So for setting up the model, we first need to unzip the files. We did this already. You should open all the Excel files. I won't do this setting up because I've done it already, but you can just follow the instructions here in the README file. So please open your Excel files, and you may get some warnings, so you can just ignore them and click at Don't Update. And you may get some warnings if your macros are not enabled. So to enable your macros, you can follow this instruction here using the Excel option tool. You should make sure that your decimal separators in Excel are correct, so that it's a dot and not a comma. You can change this under Files, Options, and then Advanced. And if you've done this, you should save and close the Excel files. Then you must make sure that the decimal separators are also correct in your Windows settings using this instruction here, so that everything goes in line. Then we must change our path in our 1IAM file using the text editor. So we can go here to the file and edit it. At the moment, it's like the former path, which you have to exchange with the path you want to use at the moment. I will also do it. So change what was done here before, and enter your own path and save the file. Then you must, if you haven't done it yet, download and install the library for the Intel Fortran. And you can just follow the instructions when you click at this link. And if you've done it, or you have to install it, or you had to install it, then you have to restart your computer. Since I've done it before, I won't show it here. So then we can come to the part where we can run the model. So as I said, the model is executable in Excel, and therefore we have like 3 different Excel files, as I said before, which are important for us. First, we have the figures file. I will show it to you. Here, we have the simulation of Lake Erie, the one that was published before. It was the Bloom from 2014, and the file here shows the data model comparison. So the data are the dots and the model simulation are the different lines for biomass, toxic fraction, microcystin, hydrogen peroxide, and the nutrients. So this is where the model simulation is depicted. The input and output of the model is written into the 1F2 file. I will also show it and walk you through the different sheets that we do have within this file. So in general, we have sheets which start with an in, so these are the input files, and with an out, these are the output files. The in are the ones for the one controller. For instance, we have the parameter tEnd, which stays, I think, for time end. So it runs at the moment for 140 days. If you want change the simulation time, you can change the value within this cell. Also an important parameter is this one here in row 14 and 15, and min. These are the agent numbers. So in this case, the simulation runs with 100 agents. This takes, for the Lake Erie simulation, more or less 30 minutes. If you want to decrease the variability of your simulation, you have to increase the agent number. For instance, 1000 agents, I think, is quite a good number, but then the runtime, of course, also increases up to 6 hours or more. So here you can change the agent number. In general, you can change all values in cells which have a green color. So here you can change everything. Also, if you change, like go from one system to another system. Here, for example, in the water column segmentation section here, you define the area that you're simulating, and also here the H, for instance, is the depth of your, or the mean depth of your system, in this case almost 6 meters. In the in-C sheet, we have the parameters which are important for the simulation of the microcystis cells. So you see already that we have now two columns, D and E. The one on the left side, D, are the parameters for the toxigenic strain, and E for the non-toxigenic strain. They should be identical, so they copy-paste each other. So in this sheet we have almost 500 parameters, or not at all, but many parameters which are important for simulating the metabolism of the cells. Here, for instance, we have transcriptation and translation of different genes. Exactly. And then we have the uptake of NO2 and NO3. In general, the Go-Gut cycle, the N cycle, is quite complex, and it's simulated at quite a distinct way. So we have many parameters for this. When we go down, we get to other sections. Here I want to just mention that, for instance, here we have the section heterocyst differentiation, which of course is not true for the microcystis model, as microcystis don't have heterocysts. This is kind of a leftover from a former model. So the Anabina model, which was also published by Helwig et al., simulated Anabina, so other cyanobacteria which form heterocysts. But we can be sure that within the code, these sections, so the heterocyst differentiation and development, is not included, so don't be confused. Here, for example, we have a section for the photosynthesis. Here we have the parameter T-opt, so the temperature optimum. In this case, it's 22 for both strains, but you can change it depending on your on your system. In general, all the parameters are described in the supplementary information file from Helwig et al. From 2022, so you can find all the parameters and the values and the ranges which can be applied in this SI, and also description of the parameters and the equations of those. So we have one differentiation between the toxigenic and the non-toxigenic strain, and this is the strategy to deal with oxidative stress. The toxigenic strain produces microcystins, and those serve as protection against oxidative stress, so they can bind to certain proteins and thereby protect them from damage by hydrogen peroxide. This is shown here in this MC synthesis in this section here. And also here you can change the parameters accordingly, but in this case the code only uses the parameters for the toxigenic strain. They are not enabled for the non-toxigenic strain, although here are certain values in this row. For instance, also in this case, it's unfortunately not in the right section, but you can see here in this row 466 we have the T-opt MCYD, so this is the temperature optimum for the MCYD synthesis, so the translation of the gene cluster which is relevant for the MC synthesis. In this case it's higher than 23 degrees than the temperature optimum for the biomass. The non-toxigenic strain has the strategy for dealing with the oxidative stress to actively degrade hydrogen peroxide using, in this case, the representative, the T2PRX gene. This is a peroxyredoxine protein which actively degrades hydrogen peroxide, and the parameters for this are here on the right hand side in the second column. So you can also change this accordingly to the ranges which are discovered and depending on your system. In the next sheet, in D, we have parameters for POM and DOM, hydrolyzation or mineralization, so the weight of those parameters for every day or per day. In B, we have the boundary condition, inflow and precipitation within, in this case is not important. And in C we have the initial condition, so the starting condition, for instance for carbon and for ammonium and nitrate. In this case we have, for example, for ammonium initial concentration of 0.15 micromole, but if you change to a different system you might adjust it accordingly. In T is the sheet for time variable input, which we can see here in the first column. We have the time steps, in the second the date, and then following time variable input. For instance, Qin is the inflow, which might change when you change to different systems. And also, for instance, F is important, the input for temperature. So if you know the temperature for your system and change from Lake Erie system to a different system or even a different year, you may have varying temperature input, and you may change this by typing it into this column here, or interpolate values if you don't have it in this time step. Also important here, the input for light or irradiance here, and other nutrients like ammonium nitrate, phosphorus. In the P file we have the input variables for our starting cyanobacterial community, which may also shift when you go to a different system, so you can also change parameters here. Yeah, and I think these are all the input parameters that you may adjust accordingly depending on the system or the dataset that you are using. When we now want to run the model, we can check again on the README file what we need to do. So we need to open the model file now. Here in the model file, we can open the Visual Basic and there use this to run the code. So we go to View Code, in the models file to the modules, and here the model code. And as also written here in the README file, we can go to the script run all and here start the run. Here with the upper button. If I would press the button, the simulation would start using all the parameters and the initial condition that I just defined in my 1F12. I won't do it because it runs for more than or like half an hour. If I would have done it, yeah, the model is simulating like these 140 days and the Microcystis dynamics within this time series, and printed into the 1F2 sheet. You could just try if the model runs correctly and makes a different output than it actually is by changing random numbers. So at the moment we see this simulation of the Lake Erie bloom. You can change the random number seed in our sheet in the 1F2 file here with this parameter rs random number seed from 1 to any other number, which changes just random numbers within the simulation, and this should change also the output, which is here depicted with this line. So you should get like a slightly different output, which does not really change in a general pattern. So you should still see these 3 peaks here in the biomass, but have a slightly different magnitude. Yes, so once the model has run, it writes all the information in the output sheets. So out R1 and 2, out R has the output for different time steps from the environmental condition, POC, DOC, for example. Out RA1 and 2 has the output for the individual strains, so 1 for toxigenic and out RA2 for the non-toxigenic strain. Then we do have the outP sheet. This summarizes kind of the summarizes the output that we are interested in. For instance, again, we have here the output in the different times in the different rows, and for instance can see here now or calculated the phycocyanin from the different model simulation for the different time steps, thereby referring to the out RA and out R sheets. For instance, here the PCN phycocyanin parameter refers to, in this case, the cells in N and O row, and when we look into this files we see that it refers to out RA1 and out R1. So this is the carbon for the non-toxic, for the toxigenic and the non-toxigenic strain, which is then converted using conversion factors to the biomass here in this row B. This row B is then depicted here in our figure sheets. So if we click here on this line, we see that this actually refers to the outP file for the row B, so what I was just showing on the 1F2 file. If you are interested in other parameters, you can also write them into this sheet in the very end. We have some spare columns where you can write in your own parameter of interest, and then the model writes it into this section here. Yeah, I think this is basically it. So I hope you got some insights how to use this model and how you can also apply it to other systems by changing input parameters and variables. And I hope you get some interesting results and insights when applying this model. Thank you very much. Bye bye.